Hello everyone, and welcome to Del Monte on Science. I'm Lou Del Monte, and we're talking about the multiverse, and the name of the series is The Multiverse Doesn't Solve the Major Cosmological Problems. And we're actually up to part 3. In parts 1 and 2, we talked about and developed the theory of the multiverse, and we talked about the level 1 multiverse and the level 2 multiverse as developed by Max Tegmark, the hierarchy he developed for that. Now we're going to talk about the level 3 multiverse, and this is by far the one that will stretch your imagination, it did mine, the most. It's called U. Everett's Many Worlds Interpretation of Quantum Mechanics. Now let's talk about that. Okay, so level 3 multiverse is, this is 3, is U. Everett, U. Everett's Many Worlds of quantum mechanics. Now I'm going to tell you that this will sound unbelievable to you. So let me give you some data. There was a poll done in 1988 by L. David Robb. His name is spelled this way, and you can look this up on the internet if you want to. He did a poll, and he took 72 of the leading cosmologists of the time, and he asked them whether they believed that this was possible, that this theory was possible. 59%, so we're talking about the majority, believed that it was possible. 59% said they believed it. And something like 13% were on the fence. That's where I am. I would fall into the 13%. The others didn't believe it. Now, the ones who believed it the most tend to be either string theorists or in the field of quantum mechanics. So basically, this will sound unbelievable, but a large percentage of very high-level physicists and cosmologists believe that it can be true. So it's worth our looking at. What is U. Everett's Many Worlds of Quantum Mechanics? Well, in quantum mechanics, remember we talked about it being a statistical as far as the answers you get when you solve the equations, and that at the quantum level, we're really dealing with statistics. We really can't say with exactly both the speed and the position of an electron, for example, and that's the Heisenberg uncertainty principle. But more generally, at the quantum level, we're really dealing with statistical probabilities of what the energies are, the positions, etc. So U. Everett came along and said, well, if I get one answer that says the energy level is this, the other answer is equally valid, then in another universe, they're seeing that answer. And that's what they measure, okay? So now, need to explain a little bit about measurement in quantum mechanics. There's the Copenhagen theory, and this is the one taught most frequently in school, in college, that when you make a measurement, usually they solve a wave function in, say, Schrodinger's equation. They'll be solving for a wave function, psi, which they associate with, say, an electron in, say, the hydrogen atom. And when they solve it, they find more than one energy level. However, when they actually measure the energy, it has a distinct value. The electron has a distinct value. And what the Copenhagen theory says is that the wave function collapses at that point, and that's why you have a distinct value. So they say it collapses. U. Everett says, no, we measured this, but in another world, they measured a different, I'm going to call that, this is psi 1, they measured psi 2, and this is, they measured a different electron velocity or energy, etc., and that's equally valid, and so they saw that. So what that means is that if I flip a coin, and you and I see it come down heads, that there's another universe, according to this theory, there's another universe that says that we're watching the same coin come down tails. And that's what Hugh Everett's Many Worlds of Quantum Mechanics actually talks about. So it says the Copenhagen theory is not, even though this is the one most commonly taught, is not totally correct. You don't get collapse of the wave function. What you really get is in another universe, another you and I seeing a different value of the same entity. And this means that every time we do something, the universe splits. So we flip a coin, we see heads, the universe split, and in another universe they saw tails. Now, hard to believe, but a lot of cosmologists believe that this is, in fact, the case. And the fourth one we'll cover is very quick, actually. It's called the ultimate ensemble. Max Tegmark actually did this one. It's the ultimate ensemble. And that says anything that you can construct mathematically is postulated to exist physically. And you may say, well, that's weird. Where'd that come from? Well, it actually goes back about to 400 BC to the philosophy of Plato. And basically, Plato postulated that physical existence, any mathematical entity has a physical existence and vice versa. So it's not a new theory. But Max Tegmark said this is the ultimate ensemble because anything you can think of would fit under here. However, there are problems with the multiverse theory, and there are three of them. One is that it does not explain the original energy to create a multiverse, whether you're talking about membranes, etc., or chaotic inflation theory. We don't explain the original energy. Second, there's no conclusive evidence of a multiverse, so that's a real drawback, whereas in the Big Bang theory, we do have conclusive evidence. And critics argue it's not good science, as I mentioned initially, that basically we're postulating a multiverse to explain, and that we can't measure, to explain a universe that we can measure. So with that, I'll leave you. Thank you very much for watching.